Okay, so let's talk about Cesaro Summation. Okay, so we consider a sequence AN, and we will define SK equals A1 until AK. So SK is the kth partial sum of a series AN. So then we will consider um, this series to be Cesaro summable if this limit exists. And it gives a number A. Okay, so one can prove that any conversion series is Cesaro summable and the sum gives the same number. But um, there are some series that diverge in the usual way, but not when we do the Cesaro summation. A classic example, it's the sum we consider an equals minus 1 and plus 1. This would be 1 minus 1, 1 minus 1, etc. So on. And this series clearly does not converge in the usual way, but if we consider the partial sums, we will have 1, then 0, 1, then 0, so they will never converge in the usual way. But if we consider the Cesaro summation, so now we will have first we will have 1 over n equal 1, it will be 0 plus 1, it will be 1, and now n will be equal to 2. Then it will be 1 again, and we have to make the sum with all the terms that happened before, and so then we have 2, n will be equal to 3, this will stay the same, and so on. So this limit now one can calculate it, because now we will have two subsequences. One that always is a half, and then we will have another one that will be k over 2k minus 1. So one can prove that this summation will give 1/2. So the Cesaro summation can tell us something about some theories that diverge in the usual way of sum. Okay, so now I will change the notation and include the Fourier series into this. Let's note the Cesaro summation sigma n fx equals to 1 n plus 1. We will count now from k equals 0 and sk fx. Okay, so if now we recall what we did when we introduced the Dirichlet kernel, we can transform this or change this in the following way. We can have the integral from minus pi to pi f of I 1 over n plus 1 of the sum k equals 0 and dk is the Dirichlet kernel dy. So we only introduced the Dirichlet kernel as we did before, including the Fourier transform. Okay, and this will be equal to minus pi pi f of y f and x minus y, and this will be f and y will be the Fejer kernel. Okay, well, the Fejer kernel has to be this part. Okay, so we can write down that fn of y is 1 over m plus 1 and the sum k equals 0 and dky. Okay, so some properties of the Fejer kernel. One can prove that you can write the Fejer kernel in the following way. I'm not going to do it, but one can express the Dirichlet kernel in terms of sines and cosines. Okay, so the Fejer kernel, you can write it as the sine m plus 1 over 2y over the sine I over 2 if x is different to k pi, k always an integer, and if not, it's going to be n plus 1. X equal to 2k pi, k means an integer. So, and some properties of the Fejer kernel. First of all, is greater than 0 or equal to, then 1 over 2 pi, the integral of minus pi pi f and y is equal to 1. A third property, the limit n going to infinity. And now we're going to take this integral delta absolute value of y pi of fn y dy is equal to 0, and this is for delta positive. Okay, so the first property, one can see this by looking at this representation of the Fejer kernel, and these two properties are interesting when you take the integral from minus pi to pi, it will give you even 2 pi. But now when you consider the integral between delta and pi, take the limit, integral will give 0. This is an interesting property of the Fejer kernel. Okay, so let's consider a theorem. Okay, if a function f is in LP, p between 1 and infinity, or f is continuous and p is equal to infinity, then the limit can go to infinity. Now the notation that we are using now for the Cesaro summation of a Fourier series minus the function in norm LP will be equal to 0. So recall that this sigma n f, we define it as the Cesaro summation and k is k f x, and that when we consider as this being the Fourier series, then this was minus pi pi fy and x minus y dy. So this representation and the function in the normal p are almost equal to the same. So two things that we can say of this is that if we consider that in this series we have the information that here you have a trigonometric polynomial, then this theorem is telling you that the trigonometric polynomials are dense in LP. And another thing that is important, if f is integrable and fk, the Fourier coefficients, are equal to 0 for all k, then f is genetically 0. So if you consider this representation and every Fourier coefficient is 0, then f must be 0. Okay, so these are some properties that unifies two concepts that at first may sound different, but the Cesaro summation and the Fourier series and the Fourier transform are all related, but by all these properties.